Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to determine whether something is going to dissolve in water or carbon tetrachloride. So let's get into this. Okay, so for this problem we're asked, what would you choose to dissolve each of these substances? Would you choose water or would you choose carbon tetrachloride? So first thing we need to review is the rule of like dissolves like. So what is that rule? So when you hear like dissolves like, that is referring to how the substances that have similar characteristics or similar, in this case, similar intermolecular forces are going to dissolve and mix with each other much more easily than, say, things that don't have the same intermolecular forces. So, for example, the usual example is like polar versus nonpolar. So, in that case, the polar substances are going to mix together and non-polar substances are going to mix together because non-polar substances have similar intermolecular forces like van der Waals or London dispersion forces. And so they're going to mix well together. And non-polar substances have similar intermolecular forces like dipole-dipole interactions, hydrogen bonding, things like that. So we're looking at those similarities. So something that is nonpolar is not going to dissolve or mix very well with something that is polar, right? Because they have different intermolecular forces, and so they're not going to mix very well. So if you have molecular forces that are really strong, you tend to stick together with your own similar molecules or similar substances. Than something that has very different intermolecular forces or much weaker intermolecular forces. So let's use that. So that's a good intro or review of the rule of like dissolves like. And here we're looking at, again, intermolecular forces. And so let's look at in each of these. So water is a polar substance. So if I draw the Lewis dot structure, you'll see that I have hydrogen bonded to oxygen. Oxygen is much more electronegative than the hydrogens. If you apply Vesper theory, remember that the electron groups want to be as far apart as possible. And so we have 4 electron groups. So that's going to give an electron group geometry of tetrahedral. And so that's going to give this shape or help us determine that this shape is a bent molecule. So water is usually depicted in this way, right? We have hydrogens on this side, and then we have our lone pairs. And so it's a bent molecule because these lone pairs are pushing the hydrogens to one side of the molecule, and therefore we have polarity. Remember, polarity deals with this idea of having a positive pole and a negative pole, a positive side of the molecule and a negative side. So here we have our negative side, and here the hydrogens have a partial positive, right? Again, for those who don't know, this little squiggly S-looking thing, that's a small delta, the Greek symbol delta, smaller case, and that stands for partial. So we're talking about partial positive charges on this side, and the oxygen with its lone pairs, it has a partial negative because the oxygen is more electronegative and will draw the electron density towards itself. So water is polar. And then carbon tetrachloride, if we draw that one, so we have carbon with 4 chlorines. Each chlorine has 3 lone pairs. There's our Lewis dot structure. Again, if we apply Vesper theory to this, we have 4 electron groups. They're all bonded. So the electron group geometry is tetrahedral. The shape or molecular geometry is the same because we don't have any lone pairs on our central atom. So this is tetrahedral shape, just like this one. except, well, this one has a molecular geometry of bent, but the tetrahedral shape is applied to the electron group geometry, but that's another video. So here we have tetrahedral. So we have four of the same atoms bonded to the central atom. There's no lone pairs. They're equally spread out. All angles are 109.5 degrees. So this is a polar molecule. One side is not more polar than the other, right? So remember, the chlorines are more electronegative than the carbon. So we would have partial negative charges here. Oops. So we have partial negative charges, but so that means that the dipole moments in the bonds are all pointing towards the chlorines. And because all the angles are equal, that means that all of these polar dipole moments in the bonds cancel each other out. And so this ends up being a nonpolar molecule. So we're looking at dissolving each of these substances in both water, which is a polar substance, and tetrachloride, which is a nonpolar substance. So then, using the rule like dissolves like, we just look at what these are and see if they're closer to water or are they closer to carbon tetrachloride. So let's look at A. A is copper 2 nitrate. You can tell that this is a ionic substance, and we know that ionic substances are identified by the fact that you have a metal and a nonmetal. So here we have copper, which is a metal. That's going to be a positive ion. And here we have our nitrate ion. So it's made out of nonmetals. Now, the only example of an ionic substance that it doesn't have a metal is ammonium, anything with ammonium in it. So ammonium, if you remember, ammonium is NH4 plus. That's an ion. There's no metals here, but it is a positive ion. That's the only case in which it's not a metal. So you have to remember that ammonium is an ion, so be careful of that. But here we have a metal and a nonmetal. Dead giveaway that you have an ionic substance. Well, ionic substances are made up of ions that have charge. So that's as polar as you can get it, if we can use that term polar, right? So here we have charges on our ions. Talk about this has a charge on it, has a dipole, right? So one side is polar, has a positive charge. One side has a partial negative charge, and so there's charge there, and it's separated in the molecule. So therefore, we would expect this to dissolve in water and not in the nonpolar substance of carbon tetrachloride. So here we would say, let me use a different color, blue. So here we would say water. So that would dissolve in water. What about CS2, carbon disulfide? Let's write out the Lewis dot structure for that. First thing we want to notice is that this is a nonmetal and nonmetal. Carbon is a nonmetal, sulfur is a nonmetal. So there's no metal here. So this is not an ionic substance, it's a covalent substance. So the next thing we want to look at is it polar or nonpolar? So let's take a look. So if we write out the Lewis dot structure, right, of CS2, we would have carbon in the middle, and we would have sulfur and two sulfurs. They will both be double bonded to each other, and each of the sulfurs would have lone pairs. And so in this case, very much like oxygen, so oxygen and sulfur are in the same group, right? Sulfur is just below oxygen. So just like with carbon dioxide, right? Carbon dioxide has this Lewis dot structure. Notice that they're very similar. They're exactly the same except for sulfurs instead of oxygens, and that's to be expected because sulfur and oxygen are in the same group, so we would expect them to behave the same and form the same similar compounds. So here you'll notice Sulfur is more electronegative than carbon, so our dipole moments are going to be going towards the sulfur. But notice that carbon has no lone pairs, so that means the electron groups in the double bonds here, we have an electron group here, electron group here. According to Westerbork theory, they're going to want to get as far apart as possible, so they're going to be on opposite sides of the carbon atom, which means that these uh, equal but opposite dipole moments in the bonds are going to cancel each other out, and therefore we have a nonpolar molecule. And so that tells us that CS2 is going to dissolve in carbon tetrachloride and not in water. So we're going to say that this is, oops, let me use my blue color. So this is going to be carbon. Here, let me just write the formulas, give myself, so I don't have to take up so much space. So this is going to dissolve in carbon tetrachloride. Okay, here we have CH3COOH, right? So if you don't recognize that, that's acetic acid, right? So if you didn't recognize that, we would write out the Lewis dot structure. So Lewis dot structure looks like this. So here we have CH3 here, C with a double bond O, and then we have OH. And so here is the molecule. You notice that we have an oxygen here, we have an oxygen here. So the oxygens are more electronegative than the carbons and hydrogens. So you're going to have electron density pulled towards the oxygens. So the oxygens are pulling the electron density this way. So this is actually going to create polarity in the molecule. And this is a smaller molecule. So the CH group here is a nonpolar group, right? So carbons and hydrogens are nonpolar. But because of the oxygens, we have two oxygens. And this is a relatively small carbon group. This is going to draw the electron density this way. So this is going to have a partial negative side here. This is going to have a partial positive side. So this carbon is going to be partially positive because it's got these two oxygens bonded to it, and the oxygens are drawing the electron density away from the carbon. So that's going to create polarity in the molecule. And so therefore, based on that, we can see, well, it must dissolve in water because that's also going to be polar. And you can see also here, we have the hydrogen bonded to oxygen. Anytime you have hydrogen bonded to either oxygen, fluorine, or nitrogen, you're going to exhibit hydrogen bonding, right? But in this case here, because of the double bond here, we have resonance. So this makes this hydrogen relatively weak, right? So weaker than you would expect. And so therefore, this is an acid, and this hydrogen is going to pop off. It's going to be transferred to water molecules. So some water molecule is going to pick that up, and so it's going to take that away, leaving a negative charge on the ion. So this is a weak acid, so it's not going to do that very much. So all of that considered, we would indicate that's going to dissolve easily in water, but not so much in carbon tetrachloride. Okay, next let me write that down. So carbon tetrachloride. Okay, what about this molecule here? It has a CH3 group followed by CH2 group, 16 of them, 16 CH2 groups, another CH2 group, and then an alcohol group, an OH group. So what does that look like? Let me draw that really quick so you can kind of see what it looks like. So we have CH3. Let me draw it up. So we have H3, and we have 16 plus this one, 17 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 OH. And each of these has 2 hydrogens on the carbons, like so. Now, as I'm drawing this in, there is another way you can draw this. There's the line method, where you don't really draw the carbons and hydrogens, you just draw a line, and each bend in the line represents a carbon, and so you can figure out what the structure is from there. But I figured this would be better, more time consuming, that is, although it is more time consuming. That's what I mean to say. And 2 more. Oh my Lord, have mercy. Okay, there we go. Okay, so this is what this looks like. So you can see that, as I said, the carbon hydrogen group here is nonpolar. So you can see that this part here, all the carbon and hydrogen chain here, that's a nonpolar group. And then over here we have what is called an alcohol group. Anytime you have OH bonded in your molecular formula, not ionic, because if it's ionic, OH minus is a hydroxide ion. So we're not talking about ionic substances. So this is not the hydroxide ion. So don't mistake this OH for OH minus hydroxide. This OH group, when it's in a covalent substance like this one, it's an alcohol group. It represents alcohol, right? So anytime you have OH, it's an alcohol, right? So this is going to have more electronegativity. So the oxygen is going to draw some of the electron density here in this bond towards the oxygen. So there is some polarity in this, but because of this huge nonpolar part, also known as hydrophobic part, right? Hydro meaning water, phobic meaning the fear. So this part is hydrophobic, meaning it's not going to like water, right? It's not going to be attracted to water. So that's a huge part of this molecule. And then you have what is called the hydrophilic part, philus meaning filio meaning like love or liking. So hydrophilic means water loving, right? So here we have a hydrophilic part, very tiny hydrophilic part, very large hydrophobic part. So therefore, we would expect this to dissolve in the nonpolar substance, carbon tetrachloride, and not so much in the water, right? The polar substance of water. So, and that's mainly because of the large chain, right? So just like this does have a small, tiny part that's non-polar, but it's comparable to this part. So you do have a large, relatively large hydrophilic or polar part here. So because this is smaller, this would allow this to dissolve in water. Now, to get this to dissolve in water, if we had an alcohol group for every third carbon, so if we had an OH group on every third carbon, that would be enough to make this dissolve in water, because then we would have more polarity spread out throughout the molecule due to the OH groups. But we only have one, so that's not going to be very helpful. Okay, so then this is going to dissolve in carbon tetrachloride. So let's put CCl4 for that one. HCl, that is hydrochloric acid, HCl. It is a strong acid, meaning that it's going to dissolve or ionize completely in water. This is a weak acid, so it's going to ionize a little tiny bit in water, not so much. Most of it is going to be in this form here. But this, however, is going to ionize completely into H plus and Cl minus. So they're going to ionize, and that means that this is going to be dissolved in water. Also, you can see that chlorine is much more electronegative than hydrogen. So if we draw the bond or draw the Lewis dot structure, that would be HCl like so. And so the dipole moment would be pointing towards the chlorine, giving chlorine a partial negative, and hydrogen would have a partial positive. Notice that the dipole moment arrow has a positive on this end, indicating positive side, and then it points this way, indicating negative side. So just FYI. Okay, so then given the fact that this is polar, even if you didn't know it ionized in water, the polarity tells us that it's going to dissolve in the polar substance of water and not so much in the non-polar substance of carbon tetrachloride. And so, but we do know that when this does dissolve in water, it will ionize into its ions completely. Okay, so that would be, this is going to be water. H2O that dissolves in water. And then finally we have H2 or C2H4. So I'm going to write the Lewis dot structure. Where do I have room? I have room. I can just do it right here. So here we have C, and then we have two H's on each one. And that means we're going to have a double bond here. So this is our molecule. This is ethene. So as said before, we have carbons and hydrogens. That's the only thing we have. So this is nonpolar. So anytime you have a molecule that only has carbon and hydrogen in it, it's a nonpolar molecule because the hydrogen carbon bonds are nonpolar. Okay, so therefore, right away, we know that this is going to dissolve in carbon tetrachloride and not in water. So this is going to be CCl4. And that, ladies and gentlemen, is how you determine whether something is going to dissolve in water or if it's going to dissolve in carbon tetrachloride. That's it for this video. I hope you enjoyed the video. I hope you enjoyed the fact that I'm not wearing a hat and I am bald and I love it. Anyway, let me know what you think. If you like this video, if you enjoyed this video, if you learned from this video, please let me know by, hey, liking the video, sharing the video, hit that like button right over somewhere around here. You'll find it. It's there. I believe in you. Also, make sure that you subscribe to my channel. Help me out. It would help me out a lot if you would subscribe to the channel. And to do that, hit subscribe. And then finally, see that notification bell. Hit that notification bell. And when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, put it down below. I would be more than happy to do that for you. Thanks for joining me and have a great day.